This is the second computer session where we are slowly evolving a code into a rather fully functional one-dimensional finite difference time domain tool. In the last session, we developed the basic engine where nothing happened, and that's what was supposed to happen. In this one, we will make something happen. We want to inject the source and see what happens. So we were starting with the code that we finished in the first computer session. So let's name it Step 2. Okay. And rather than say basic fdtd engine, we will say we are adding a simple Gaussian soft source. Okay. And we'll just make the changes that we need, but the initialization stays the same, the units, the constants, and opening up of the figure window, that all stays the same. Our dashboard will change a little bit. Now that we have a source, we're going to do some things a little bit differently. So we need some source parameters. At this stage, we only need one. We'll add more later. And let's say 5 gigahertz. So this parameter is the maximum frequency that we're interested in simulating. What we need to do, as discussed in the theory slides, is make sure that our pulse source is short enough in duration to include sufficient power at this maximum frequency that we're interested in. So from Fmax, we will calculate the duration of our pulse source. Now the FDTD parameters, we will calculate them differently in a little bit. So rather than call this FDTD parameters, let's talk about grid parameters. We need to know the maximum refractive index throughout the entire grid, and we'll need this two places. We'll want to know how fast a wave is traveling, and it will be traveling its slowest inside the maximum refractive index. We also need to resolve the shortest possible wavelength. So this is the wavelength of the highest frequency inside the maximum refractive index material. So we don't have a device in here, it's just air, so our maximum refractive index, in fact, is just 1. We want to choose the distance between the points on our grid, the grid resolution. And so this parameter is exactly that. If we set it to 10, that's saying we want to resolve the shortest wavelength of the highest frequency with 10 points. Eventually, we'll have a device in our grid. And just to make things look nice and to learn from this, we want to put some space before and after that. So that's what this parameter is. We'll say 100, 100, and that means we'll put 100 points before the device and 100 points after the device. Now, of course, right now, there is no device, so that means our grid will be 200 points. Maybe we'll add a few more for other reasons. So that's it now for our dashboard. Again, as we add features in future computer sessions, we'll come back and add more here. Right after the dashboard, the first thing we'll need to do, since we deleted our FDTD parameters, is start calculating them. And the first thing is to compute an optimized grid. And the first step here is to calculate the nominal resolution. First, we need to know what is the minimum wavelength inside our simulation. We'll call that LAM 0. Well, it is the speed of light over Fmax. That will be the shortest wavelength we're interested in, the wavelength at the highest frequency. Next, we need to calculate our grid resolution. So we'll take that shortest wavelength, which is the free space wavelength, divide by the maximum refractive index because the wave slows down and the wavelength becomes even smaller, and take that quantity and divide it by the n lam, which we have set to 10. And experience shows that below 10 we don't get accurate answers, and 10 is about the threshold where our answers start to resemble reality. In fact, we'll probably need more like 20 or 40, but since we're just demonstrating the algorithm, 10 is perfectly sufficient. Now we need to calculate our grid size. How many points do we need on our grid? And we'll call that big NZ. Well, first of all, we'll add up both of the numbers that we include in the n buff z parameter. And eventually we'll add points to incorporate our device or maybe some other things that we're doing. But I'm going to add 3 more points. Eventually this will let us include places where we record transmission and reflection, inject the source, that sort of thing. So we'll include them here right now. Our grid axis. This will be an array that tells us the position of each point on our grid. So in square brackets, we're creating an array of integers that goes from 0 to the number of points minus 1. So if we have 203 points in our grid, this array will go 0, 1, 2, 3, 4, 5, all the way up to 202. We don't need to go to 203 because we're starting this at 0. We multiply that array by the grid cell size or the grid resolution, and now ZA will be an array of the position of each point in our grid along the z-axis. Let's put a break in here and run it. Make sure we haven't made any typos or mistakes. Okay, everything looks good. On to the next section. Build the device on the grid. There's no reason to change anything here. We just calculated NZ. So this will run and fill everything with free space. We do need to add another section right after that. And this is computing the source. And this will be the biggest addition to this code. There's several things we have to do here. The first one is compute the time step. And so that's the DT parameter. Now, we're going to do something that we won't include the feature until next time, but we need to know the refractive index at the boundaries, because eventually we're going to have these perfectly absorbing boundaries. In fact, I think that's the next computer session. But it's part of calculating the time step, and we need the time step, so we need to do that here. So first of all, the refractive index at the boundaries of our grid. Refractive index is square root of mu times epsilon. So we will look at the first point. We'll look at the permeability of point 1 and the permittivity of point 1. And now NBC will be the refractive index at point 1. And it's from that that we calculate our time step, which is simply that refractive index times dz over 2 times c naught. And remember what this equation is doing. It's for that perfectly absorbing boundary condition that we'll do in the next computer session. But this ensures that the wave travels one grid cell in exactly 2 time clicks. We have some parameters to calculate for the Gaussian, and specifically that is its duration and its offset. So the duration needs to be sufficient so that it includes enough power at our maximum frequency. And the equation we derived in the theory slides was 0.5 divided by F max. We need to calculate an offset. If we didn't give it any offset, at the very first time step, we'd be exactly in the middle of our Gaussian. And to turn a source on that fast is bad news. We'd rather ease into it and ease out of it. So I like to delay it by about 5 of the durations of the pulse. So the T naught is the delay. We need to compute the number of time steps. In the first computer session, we just set that to 1,000, but let's actually calculate this a little bit more intelligently now. T-prop, this will be the time it takes, in the worst case, for a wave to travel once across our grid, left to right. So that is the maximum refractive index times the length of our grid, NZ times DZ, divided by the speed.